Now coming to the function where we enable the Systick and configure it. So let's get back and to the diagram that we saw on the presentation. So we will be enabling the Systick, we'll be configuring the Systick control and status register, and we will be working with the Systick reload value register. So these are the two main registers that we are going to be working with in this particular function. And of course there is another register which is called the SHP, that is the system handler priority registers, to configure Systick. Now in the code we see three variables that I created to begin with, that is the clock source, the interrupt enable bit, and the general enable bit for Systick, and the reload value, that is the what value we intend to reload into the reload value register, and we calculated that to be this value, that is 0x280DE7 from the previous session. Now if you see here, this is the clock source bit for the Systick control and status register. So here if you choose a 0, it is a default, by default the value is 0. So if you choose a 0, it's the actual AHP, so AHP bus is connected to this side, so whatever the bus clock frequency is gets divided by 8. In our case, since it's 84 megahertz, that clock gets divided by 8 and is fed into the down counter. The second one is for enabling the Systick interrupt, and the third one is to enable the counter itself, that is enable the Systick itself. So these are the three bits, though you see a 1 here, but in our case we will need to configure it to 0. So if you want to so this one, instead of a 1, it is going to be a 0 in our case. So let us have a look at the Systick status and control register and Systick reload value register. So we need to find the registers first. So let's type Systick here. So Systick timer. So this is the Systick control and status register, and these are the 3-bit fields that we had been talking about. One is the enabling the Systick itself, another one is enabling the interrupt related to Systick, and another one is the clock source. Now the clock source is 0 by default, and that we can figure out by the reset value. So whenever you want to know what value the Systick has, control and status register has by, or any register has by default, check the reset value. So if you now interpret the reset value in terms of the bits, that is the bit that the register has, then since these values are 0 to begin with, all these values are 0. And very shortly in this function you will see a huge mistake that I had committed in the code. I have left that mistake because for you to as a reminder to you that how bugs can sneak into a code. So anyway, so this is the first register we are configuring. The second one is the Systick reload value register, which is the 24-bit register that we had been talking about, and this is the register that we have to fill our reload value into. And the third, we are not touching the Systick current value register because we don't need it. We are not reading it also. And this register has the current value of the Systick counter. So when it's counting down, this register actually has the value that it has currently holding. Okay. and this value is a dynamic value because it is constantly counting down, and a write to any value clears the field to 0 and also clears the count flag bit in the Systick control register 0. So the count flag bit, that is what you have here, it is returns a 1 if the timer counted to 0 since the last time this was read. Now suppose if you are using the Systick in polled mode, then you will need to use this to check every time whether the count flag has gone down to 0 and take the necessary steps after the count flag has been set. But in our case, since this is interrupt driven, we don't need to worry about the count flag. Automatically, when the countdown to 0 happens, the interrupt is going to be raised. A current value register, so we are not using that, and we are not even using the, this is anyway a read-only register. We are not using the calibration value register also. So now, so what is the clock source? So the clock source in our case, if you see the diagram here, we are using the divide by 8 prescaler, and that the value has to be 0. So that is what you see here. Clock source is 0, and this is a way of representing the bit pattern. We could have, so 0x0 moved by 2, okay, or if it was a 1, generally we write it like this, that is moved by 2. So this actually gives a better representation of where the bit position is. 0x1 moved by say 2 is equivalent to 0x100. Okay, so if this were a 1, we could have also written it this way, but it really does not convey the meaning of this particular line. So it's a good practice to actually write it this way, so that we know that this is in the second bit. Second position means 0, 1, 2 means the third bit or the bit number 2. Similarly, interrupt enable is at bit number 1, as you can see from here. So interrupt enable is at bit number 1. So we are moving that bit to the first position, and enable is 1 move to 0, that is it is in the 0th position. So it conveys the meaning which position the bit is in through by writing it using the left shift operator. And then we have seen this reload value from our previous session. Now this is where you set the Systick priority. Now we have only defined the values. We have not yet filled the registers with these values. So this is just defining the values. So second is we do a Systick priority equal to 0x04 shifted by 4. So definitely we are setting up the priority of the Systick interrupt to be 4, and whichever is the priority register, we are shifting it by 4. So now the reason why we are shifting it by 4 is, as we discussed, the upper 4 bits are used for priority calculations. Okay, the lower 4 bits are not used. That is the reason when we set the priority, we have to move it up by 4 bits like this. Thus you see it here. Okay. Now, then the next line is ASM volatile CPSID I. Now we talked about this. This actually sets the bit in the primask register. So the primask register actually disables all interrupts with configurable priority. Now we do this because this is a very critical section of the code when we are setting up the timer. So we don't want other interrupts of a configurable priority to disturb this particular part of the code. When the control is moving through this code, it should not be disturbed. So that is the reason why we use CPSID I, and we used to have to use as ASM volatile because this is this register cannot be accessed using the address map. Now we set the priority here. So we say that Systick priority SHP 11. So let us have a look at the Systick priority register now. So we go into our data sheet and then we type for SHP. So we go here and we type SHP. So this is the system handler priority registers. Now this is within the system control block that you can figure out from here. So it's SCB, so that's within the system control block. So these are internal to the Cortex M4 core. It's generic as we discussed. So this is not in the NVIC. However, the priority of this these priorities will interact with the priorities in the NVIC. So these don't sit in a silo. They interact with the NVIC. Now here are the system fault handler priority fields, and here are 3 registers which set up the priority for the exceptions actually. That is in the first part, that is the system exceptions. If you look at the registers, they are of course 32-bit registers, and every 8-bit, so this is one 8-bit, stands for one particular exception. For example, say priority 4 is memory management fault. So this is the priority 4. So it starts from priority 4. Okay, that is it starts from the memory management fault exception. Okay, so you cannot set the priority of the exceptions above this. Okay, so it starts from this. Then the priority 5 here is the bus fault exception. Priority 6 is the usage fault exception. Okay, now if you go further down, so this is the first register. So go further down, we have the system handler priority 2 register. Now the priority 2 register it only handles the SV call. So SV call again is in the position. So you have to keep in mind the position of the byte. So this is 1 byte, and lower 4 bits are read only, because we know that only the upper 4 bits are used for setting the priority. Now since the lower 4 bits are read, we have to, as you saw, there's a shift by 4 done. Now this is reserved. Even though this is reserved, when calculating the bit position, of course this space has to be considered. That is, we have, when we will access it, these registers are byte accessible, and we will have to consider these spaces also. For example, this is 1. Okay, this is so in the array, this is position 0, position 1, position 2. Position 3 is reserved. Again here in the second register, position 4 is reserved, position 5 is reserved, position 6 is reserved. So again in position 7 you can write some value. Here again in the system handler priority register 3, we have the first 2 positions reserved, and this one is the priority 15. Okay, so you can see this is 11, and then it jumps to 14, and then it goes to 15. But this one is the 12th position. Okay. 3 registers, each comprising of 4 bytes. So obviously this is so our Systick exception is in the 12th position. So this is the 11th byte if you consider it a part of an array. Okay. So now that is what is going on here. So you have SCB, SHP 11, so system control block SHP. These are the SHP registers, and since these are byte addressable, we do SHP 11 means this is actually the 12th position. So this is the 11th byte we say, and we are putting in the priority value, and the priority value is again shifted by 4. Then we are setting the reload value, that is in the Systick load register. So we saw the reload value register. So this is in CMSIS header. It is termed as a Systick load. So we are loading the reload value here. After we are loading the reload value, we are clearing this field. Now, when I wrote the code, so this I have to discuss about this. So when I wrote the code in the beginning, I was not aware that a 0.25 second timeout is not possible with a 84 megahertz clock. Okay, because it exceeds the 24-bit boundary. Now, I wasn't aware of that, and when I started the code, I actually made it a 1 here. Okay, and later on I made it a 0 here. Now what I assumed here when I came to this line of the code, okay, Systick CTRL, so since we have to clear the fields, since it was a 1 previously, if you OR these three, enable intent and clock source, to in the previous case this was 0 0 0 0, so it is 0 0 1 0 1 0 and 1 0 0. So this would have been 1 1 1 if you ORed all these three together. Okay, and that was the assumption under which I cleared this field using these three variables only. And it seemed to work, and the clock seemed to work, but you see the mistake that I had committed here. The mistake was in the later case, when I AND it with enable, int enable and clock source, the value is actually 0 1 1. Okay, not 1 1 1, because this is 0 moved to two spaces. So 0 moved to two places is 0 0 0. Then this one is 0 1 0 and this one is 0 0 1. So I was thinking that here, carelessly, I was thinking that I was actually ANDing it with a 1 1 1. So basically this was ANDing with a 0 1 1. So ANDing and clearing the fields. So if you come here, so if you come to the, we'll go back to the Systick register once again and I'll show you what was really going on here. So Systick status and control register, here I was ANDing it with, mistakenly I was ANDing it with a 0 1 1, ANDing it with the complement of 0 1 1. Okay, so what was the value that it was actually getting? It was ideally I had to AND it with a 1 1 1 to clear these fields, but I was ANDing it with a 0 1 1, but I was still getting the right value. That was because I was lucky that the reset value was 0. So since the reset value was 0, even if I did an AND with the complement of 0 1 1, the value came out to be 0 0 0 and my Systick worked. By any chance, if any of these values had been especially if the clock source value had been a 1 by default, okay, say it was not a 0 but a 1 by default, I would be getting when I clear the fields, instead of 0 0 0, I would be getting a 1 0 0. And in the next line, when I'm just doing an OR, so enable here or the enable or the clock source here was the value 0 0 0 now. Okay, so or the clock source value is 0 0 0 now, and if this value was a 1, because we failed to clear it previously, the clock source would remain as a 1. If the clock source remained as a 1, it would be using the faster clock, that is, it would be using the bus clock. It will not be passing it through the prescaler, and you would see that the timer is, or the Systick timer is timing out much faster, 8 times faster, and you would begin to wonder what is really going on. Now the code that you download for practice will have this corrected. So ideally, whenever you are clearing the bit field, don't do what I did here. What you need to do is you need to use a specific bit pattern. So you may you may declare a variable and assign a bit pattern to the variable and put the variable here. That is, you can do U9032 underscore T clear CTRL, and then set a bit pattern, say 0B111, and then in this case, so you can put, ideally the convention is putting this in caps, but yeah, you could do, instead of clearing this, you could put clear control here. Okay, never use the bits that you are using to configure a register to clear the registers. Okay, use a separate set of bits, otherwise such problems will happen. Now if I overlook this problem, it would you would start using this code, and if you need to use this particular function, or if you need to use this particular style to clear a field, you are going to, and that field has a default value of 1, your code is going to come up with a bug. And now I was lucky that even with that, the code was operating properly because of the default value 0. So these are some subtle bugs that you are definitely going to encounter when you do your microcontroller coding, and I thought that I will leave this problem behind for you to see. Of course, the downloaded code that you have that you are going to see will have something like this. So it is going to have these bit fields will be cleared properly. But then this is a good lesson and a reminder for all of you to be careful about these bitwise operations. So now, assuming that all the bits are cleared, what we do is we do int enable and clock source. So this, we do this 0, 0, 0, 0, 1, 0 and 0, 0, 1. So what we get is 0, 1, 1. So we OR this field with 0, 1, 1. So when we OR it with 0, 1, 1, what we get is this 0, 1, 1 in this register, Systick control and status register, which you also saw in the data sheet. Once you get that, this register is all set to operate. So the moment you set this, the Systick timer is activated. It starts counting down, and then you do ASM volatile CPSIE I. So this means you have enabled that enabled all the interrupts with configurable priority now. That is, you have again in the primask register, you have enabled all interrupts with configurable priority. So now all the interrupts can again start functioning. There could be interrupts which come within this within the execution of this code. Since those such interrupts are disabled, say interrupts coming from NVIC, such interrupts are disabled, they will go into the pending state and only be activated after CPSIEI. And there is some more there are some more nuances here. That is, there are certain commands like ISB, okay, which actually clears the pipeline, and you need to do it in some cases, okay, where if you want that interrupt, that is a pending interrupt that has come here, to immediately execute without executing the instructions on the pipeline, then you need to even use the ISB instruction here, and I have talked about that little later. Okay, so I have explained why the ISB instruction is needed. So that configures your Systick. Next, we'll see how to write the interrupt service routine. So interrupt service routine is very straightforward. It's just like any other function. And ARM Cortex M4, as you know, gives you the provision of writing the interrupt service routine just like an ordinary function. So you don't need to bother about informing the compiler that it's an interrupt service routine or anything. It's automatically handled by the hardware. This enables the Systick. So what happens is, in the main, you have to call the enable Systick. So generally, if you are configuring the Systick interrupt, this is what you will need. You will you'll need to initialize the PLL, because all the so depending on the processor frequency, again your Systick count will vary, right? So if it is 80 megahertz, or if it's 60 megahertz or 50 megahertz, you have to do the calculation all over again, and your count is going to vary for the Systick interrupt. So this is whatever we saw is dependent on the processor clock again. This was considering that the clock is 84 megahertz. We have other calls here, which is not directly related to Systick, but these are the calls that we are making for the other purposes. For example, there is this call where we do enable LED. Now I'm just thinking that let us not talk about enabling the LED here, because we have discussed it in the IO section already. So you know how the LEDs are enabled anyway. So we'll not talk about enabling the LEDs, or we'll not talk about configuring the user button, because these are typical IO operations. So we will only focus on enabling the interrupts for Systick, and in the next section we will talk about configuring the EXTI0. So we will mention it in passing about setting up the ports as they should be, but will not emphasize on them in this case. So now once we have configured the Systick, we have to go and actually write the Systick handler. Now Cortex-M4 makes it extremely easy to actually write the Systick handler. So now let us have a look at the Systick interrupt, and it's very easy to write the interrupt because it is just like any other function here. So since the Cortex-M4, as we discussed, takes care of a lot of activities of saving and restoring the registers and so on. Once we configure the interrupt, writing the handler is just like any other function. So you will not see anything specific or any other attributes that need to be added to this function saying it's an interrupt or so on and so forth. So this is just a plain function. So we write the Systick handler, and this is what we have entered in the startup file. That is Systick handler here, and we just toggle the LED. So the LED that we toggle is actually the blue LED on the board. And this is what we do. So let's say it's the blue LED, it's not the orange LED. And of course, the EXTI0 handler does something very interesting. When we get into the handler here, we will see that how when we have seen the preemption example. So now we will actually have a look at in the next lessons, we will see how we are setting up the INTI0 handler. So anyway, so this is just toggling the blue LED. That's all the Systick handler does, and it toggles the LED every 0.25 seconds. So obviously so if it's 0.25 seconds, so the LED goes on. So it goes on. So say if the LED goes on at 0th second, it goes off at, because it is toggling, okay, it goes off at 0.25 seconds, and it goes on again at 0.5 seconds, right? So the duration between two ons is 0.5 seconds. That is why when you see on the board, when the LED starts toggling, you'll see that the LED is toggling at half a second. That is, LED is blinking at half second interval. Okay. If you did not toggle the LED, and if you just blinked the LED, then you will see that it is blinking much faster. Here we have just done a toggle, and all of this is left from the previous examples that we saw. That is the preemption examples that we saw. So NVIC, STI. So this is something that I have not shown you. You can try that out yourself, or we'll see it sometime. We triggered the interrupt through software here, right? That is through NVIC we triggered the pending status. In fact, the pending status can be also triggered through the STIR interrupt. So this is where we did. So if you give the interrupt number, the same thing happens. Instead of here, if you give the interrupt number, this also sets the pending status of the interrupt that you want. So that is also another way by which you can trigger the interrupt. ISB instruction is it's a special instruction to clear the pipeline. Now the way I have used the ISB instruction in this interrupt handler is not the conventional way. I have just used it as a substitute to the NOP operation. So instead of the NOP, I have used the ISB instruction here. Ideally, in the context of interrupts, ISB should be used this way. So suppose you are so let's go here. Let's go on top. So we have used some CPSIE and CPSID instructions when we were setting up the interrupts, if you remember. For example, this one, CPSIE and CPSID, right? So basically, ISB instructions are to be used in those places. Generally, I have used it just as a replacement for NOP. It doesn't hurt to use it like that, but generally it is used in those places. Now this is the reason. When you have a CPSIE instruction executed, so suppose we did a CPSID instruction before, and that is to disable all interrupts. We saw that before, when we are setting up some interrupt, we disable all interrupts so that no interrupts disturbed the settings which we did. So we saw that before. For example, here when we did a CPSID, that is, we disabled the interrupt for setting up the Systick, and then we did all the configuration and we enabled the interrupt here so that this one was not disturbed. This setting was not disturbed. But let's assume within this interval, some interrupt comes in. Not the Systick, because the Systick is not even configured. But at this point, within this point, if some interrupts come in, so let's say that between CPSID and CPSIE, let's draw this. So we have, say, this is the timeline, suppose, within which no interrupt should occur. But say an interrupt came in and it went into the pending state. Of course, it will not be executed, but it will go into the pending state. Even though interrupts are disabled, it can still go into the pending state. So now, in this particular scenario, when the CPSIE instruction is executed, the instruction that is in the pending state may or may not execute immediately after. So there will be an instruction, say first instruction, second instruction, third instruction. So the interrupt might execute here. So these are instructions in the pipeline. Suppose the pending interrupt might be serviced here. Okay. So generally what is done is, there is an ISB instruction that is issued, okay, so that this pipeline is flushed and the pending instruction gets executed immediately. So generally the ISB instruction should be coming here. So it should be ASM ISB. Since we do not have a requirement of immediately executing a pending interrupt after CPSIE, we don't have an ASM ISB here, but that is the use of ISB. ISB instruction has a lot of other applications. The other memory barrier instruction should be used sparingly. They have their own applications, but they are used in some specific cases, so they are not used all the time. It is These instructions are not as common as you would as uh, the other instructions that we use very often. So that is the use of the ISB instruction. Now we'll see a demo of the LED blinking every half a second, because for the Systick, because the toggle is for 0.25 seconds, so the LED is going to blink for half a second, and we are going to see a short video of that, of the LED blinking. Now if you really want to ensure that the LED is blinking every half a second, what you can do is you can hold a stopwatch and for your board, and maybe you can take the timing for 10 or 20 blinks and then divide it by that many blinks, divided by 20, and you will see your that you get around 0.5 seconds in that case. And now we will go into the EXTI0 handler setup and run. I mistakenly named this as INTI0 handler. So this is going to be called as a EXTI. So we are going to change the function names and everything. And the overall method of setting this up is pretty much the same as Systick, but definitely the registers that need to be configured are different.